This video is the start of our series on gravity. And I think one common misconception that people have, or question that people have, is gravity caused by the Earth's rotation? In other words, is it because the Earth is spinning? And the answer to that is no. So, for example, if a person goes to the South Pole, you can do that. You can go to the South Pole. You can visit the penguins. I think there was somebody who walked across the South Pole. No problem. Because it's not the spinning of the Earth causing the gravity. It's the mass of the Earth. And that gravitational pull is always in towards the center. Whether you're on the equator, Pennsylvania's probably right around there. There's the North Pole. No matter where you are, there's still gravity. Another reasonable question to ask might be, well, what if the Earth stops rotating? I mean, it's not going to, but if it did, you would not float off into space. The mass of the Earth would keep you right where you are. Which brings us to Newton's law of universal gravitation. Every object in the universe is attracted to every other object, and it's based on mass. So something really heavy like the Earth has a strong gravitational pull. Jupiter even more. The Sun even more. The heavier a mass is, the more force of gravity there's going to be between it and another object. But the force drops off very quickly with the distance squared. So if we took a look at that, if we took a look at the force versus the radius, we would see that it's at exponential decay. Now, it never really quite goes to zero. There's an asymptote here. But as you get further and further away, it becomes essentially zero. So every object in the universe is still attracted to every other object. Like we think, okay, well, we're attracted to the Earth. We understand that. But as I'm sitting here recording this, I can see my mug here. My mug and I are actually gravitationally attracted to one another. So you might say, well, why doesn't the mug, leap off the table and come stick to me? Well, there's friction because of gravity, because the pull of the Earth is so much stronger. I'm not going to be able to move it. But if my mug and I were in outer space, I was in a spacesuit so I don't die, and I let the mug go, and I stood there, after a while, the mug and I would move towards each other. Now, it's not just that the mug would move towards me, I would move as well. The mug will move more because it weighs it has so much less mass than I do, but I would move because every object is attracted to every other one, as you can see in this cartoon here. At least she was still attracted to him gravitationally. So here's the formula. F is g mm over r squared. Now, what's the g and what's the m? And in fact, as I'm talking, I'm going to put the g stored in my calculator because we're going to use it so much, and I don't want to have to type it in all the time. G is the gravitational constant for the universe. And as far as we know, that's exactly the same everywhere in the universe. That's a pretty small number, 10 to the minus 11. Of the four forces, gravity, electromagnetism, and the strong and weak nuclear force, those are the only four forces in the universe, gravity is the weakest. You can beat gravity. You do it all the time. I bet on your refrigerator and my refrigerator you have a few pieces of paper with magnets. They don't fall to the ground. The magnetism is much, much stronger than what gravity is. Now, I like big M for the heavier object and little m for the smaller object. Some books and some places are going to use M1 and M2, but then you have to use the subscripts. Certainly they're not wrong. I think a capital M and a small m is just easier. And r is the distance. It's an inverse square relationship. As you move further and further away, it drops off quickly and quickly, and that's also true for electric charge. And a scientist by the name of Cavendish actually proved this. Newton couldn't measure G. He just didn't have sensitive enough equipment way back when to actually carefully measure G. So it took a while till a scientist by the name of Cavendish did, and he did it by having two balls or spheres, and then he would bring another one in close, and the whole apparatus would swing a little bit. And measuring the angle that it swung, he could have an idea of, well, what G should be. Now, we think about, well, we're kept in orbit around the sun, but the other planets pull on us as well. However, the sun is just so much more massive that it doesn't really matter. But it is worth pointing out that everything in the solar system pulls on everything else. An example might be our tides. The moon pulls on the Earth. Now, the moon is much smaller than, say, Saturn or Jupiter, but the moon is also a lot closer, so that's why it has that tidal effect on us. And just to give you an idea how big the sun is, this is an old black and white drawing, but I think it shows it perfectly. If we put all the other planets, and they were still calling Pluto a planet way back when, but it doesn't matter. If we put all the other planets, all the asteroids, everything else inside the sun is still that much more massive. It's just unbelievably massive. I use the example of if it was just one person and they ate one McDonald's hamburger. The person would be the sun, and the McDonald's hamburger would be everything else in the solar system. Yeah, you'd notice if you ate a hamburger, but not that much. And here's another really old picture, but it shows it kind of nicely, that the moon is about 1/81st, or it would take 81 moons to equal the mass of the Earth. And that was a video. I'm not going to show you that right now. So let's see what the force of gravity is between two 60-kilogram people. That's 132 pounds. So that's not a bad average for a high school student. We're going to have them stand 2 meters apart. So this might be, you're standing and you're about 2 meters away from somebody in the cafeteria line. So F is G mm over r squared. So G is that 6.67 times 10 to the minus 11th. 60 kilograms. We're 2 meters apart, but we're going to square that. And we can calculate it, and we get a force of 6 times 10 to the minus 8th newtons. That's a really small force. That force is so small, I'm not even sure how easily we could measure that between two people. So the two people are 2 meters apart, but there is a force. However, that force, and it's the same force on both of them. It's not like one is causing the force on the other. They both cause the force on each other. But it's so small that it will never pull them together. It's just not in any way strong enough to do that. And the last thing that we'll finish off with today is we say, well, what about that person and the Earth? And I give you the radius of the Earth and the mass of the Earth. So again, we go back to Newton's law of universal gravitation. Let me get the person out of the way here. But we have to put in the G. Now look at the mass of the Earth, 5.98 times 10 to the 24th. That's big M. The 60-kilogram person, that's little m. And then there's the distance. So when you measure these distances, you measure them from the center of the Earth. That's the radius. We get 588 newtons. That's a whole lot more than something that's times 10 to the 8. And watch this. What if we calculate the person's weight? Weight's mg, 60 kilograms times 9.8. And let's see what we get. And we shouldn't be surprised at the number we get. We get 588. Wasn't it a lot easier to calculate it using weight rather than using Newton's law of universal gravitation? But they're the same. The gravity between the Earth and the person is what causes our weight.